This is part 2 of chapter 8 on smoothing interpreted in the time and frequency domain. So now we're going to move on to considering estimating trend by Lowpass smoothing. Lowpass is a local linear regression approach, and it's unclear exactly what the acronym is. Perhaps it's local estimation by smoothing, and it's also the same algorithm is also known as Lowpass, spelled differently with a W, which could be locally weighted sum of squares. Anyway, here's what the Lowpass algorithm does. At each point in time, you compute a linear regression, which could be constant linear or quadratic model fit by least squares using only neighboring times. And so you can think of this as a moving window of points included in the regression. And maybe it's simplest to draw a picture here. So if you have a scatter plot of points, and you want to know what is the smooth value at this point of time, you take a window this is my window, and then you do a least squares fit based on points in that window, and then you evaluate that at this center point, and that is the Lowpass value of the smoother at that point. And Lowpass is implemented in R by the function Lowpass, and exactly how to weight these points is done by something called a span argument, which is essentially the fraction of points that's included in the window. Now, the question with smoothing is always, how do you choose the this span argument, the smoothing parameter? Well, oftentimes in practice, you do it by eye, and we're going to start by looking for a value of span that visually separates long-term trend from business cycle. And here is such a thing. I just played around and decided that a span of 0.5 seemed to me to produce something that looked like a trend for these data. And here we go. We've got a smooth trend in black, and the unemployment data in red. And you can see from this that there was, according to this trend estimate, there was sort of structurally higher unemployment in the 1980s. That might be something that fits with your view of economic history. Now, when you choose a smoothing parameter by eye, there's always the question, what did you actually do? What has this smoother done to the different frequencies? And so here we're going to compute the frequency response function for the smoother that we considered there, and we'll see which frequencies it cuts out and which it doesn't. So the code here is very much what we've seen before, except now we're comparing the raw data with the smooth data. Here we go, and I've put a horizontal red line at 1, and how are we going to describe what this filter has done? Well, this filter is, like most smoothers, it's what we call a low-pass filter. That means it lets low frequencies through. power at frequencies higher than, well, let's pick a point here. This is about 0.1. Let's say 0.1 cycles per year, which is of course a 10-year cycle. A reduced by 2 orders of magnitude. Or more. Okay, and this just, this means that our trend estimate is really getting the longer term components of things that are reasonably fixed on a decadal scale. Now, if we want to extract business cycles, we might think that these really low frequencies are kind of structural changes in the economy. High frequency variation is noise, and somewhere in the middle, we might get business cycle frequencies. And so now we've extracted off a trend for the more structural component. We can subtract off an estimate of the high frequency component by using a much smaller span here of 0.1, and we can see what we're left with. This is sometimes called a trend noise cycle decomposition of the data. And here we go. U1 is the original unemployment data. U2 low is this long-term trend. U cycles is our cycle estimate, and U high is all the noise that's left over. And I think, looking at this, it seems to have done a reasonable job of breaking up the time series. If you sum the 3 lower ones, you get the top one. And it seems to have broken up the time series into different parts with some distinctly different characteristics. Now, again, we might want to understand what have we done when we've done this. We've identified something as business cycle frequencies, but exactly those frequencies we pulled out, we haven't discovered business cycles necessarily. We've defined a range of frequency components that we're calling business cycles. And that's actually a property of the smoothing procedure rather than the data. But let's see what frequencies we pulled out. Well, here we've done another frequency response function, this time for the business cycle frequencies. And let's look at what we get from that procedure. Units of frequency are emitted, but this had better be in cycles per year. If it were in cycles per month, that would only go up to a half for monthly data. Okay, and let's see what we can say about this. Maybe say here, here we keep at least half the power for frequencies with cycle length between well, the high frequency is 1 over 0.201, which is approximately 5 years. And 1 over 0.058, which is whatever it is, about 15 years. So we have to choose some arbitrary cutoff. I chose a half as our measure of the range we're interested in. That's kind of like you use half-life when you're studying nuclear decay, for example. You need to choose some arbitrary constant for your cutoff. Now, right, as I mentioned on the previous graph, when we looked at the frequencies that this business cycle estimation procedure pulled out, that was determined by the smoothing procedure rather than necessarily driven by a true property of the data. Let's go back to the original data and look at a smooth periodogram for raw unemployment data plotted up to 0.7 cycles per year. That's because we don't think business cycles are not going to be much shorter than a year. We're not interested in real high frequency effects here. And we want to not worry about seasonality issues, at least in this plot. So what does this say about the evidence for and against the concept of a business cycle in the data? Well, I think when you look at this smooth periodogram, it should kind of make you question to what extent real characteristic business cycle frequencies exist. So let's say there are no clear peaks in the estimated spectrum. I'm not saying that boom and bust cycles don't happen. Boom and bust cycles do happen, but obviously they have unpredictable duration. In physics, you would call this a resonant frequency. There are not resonant frequencies associated with the economy. You could also argue that there are resonant frequencies, but the government does such a good job of damping them down by policy. So I guess there are always alternative explanations. So here we focused on low S, but there are other similar options that you can play with. They're functionally fairly equivalent, and I find low S convenient, so I'm going to focus on that one. But just in case you see others around, you can do kernel smoothing where it kind of fits a nice Gaussian kernel at each point, and you can also fit splines at each to the time series, try and estimate the mean. You're very welcome to read about them. You can try them if you want, but we won't get into them further at this point. So when you have a smoother, there's always some smoothing parameter, and often that's called a bandwidth. The bandwidth measures the size of the neighborhood of time points where that's used to estimate the smooth value at some particular target time point. The concept of bandwidth is most obvious for kernel smoothers, because in kernel smoothers, you're kind of exactly using some kernel to describe the local neighborhoods that you're looking at for the smoothing. But you can, all smoothers have some such localization idea. We usually only interpret bandwidth up to a constant. So generally, the larger the bandwidth, the larger the neighborhood you're smoothing over. Smaller bandwidth means less smoothing, so a more bumpy estimate of the expected value. So I think when you're using these methods, rather than focusing on the bandwidth, you focus on the tuning parameter for the algorithm you're actually using, which, unless you're doing kernel smoothing, is probably something different from the bandwidth. They just calculate something that they call a bandwidth in case you want to interpret it, but we're not interpreting that much here. So there you go. We've introduced smoothers, and they're useful things. You can go ahead and play with them.